Welcome to the 10th grade algebra. For this one, we will discuss about sets of numbers. It is from the first chapter, the preliminary information, and I will go to the definition of each as sets of numbers so we can identify number to which sets of number it belongs to. I will use the tree diagram on the textbook that we use as the reference. So I will start with the lowest level, which I called as the first level. And the first level, the first set of number that we'll discuss is the counting numbers or natural numbers. So please be aware that counting and natural numbers are just the same. Okay, you can use the name interchangeably, and the symbol itself it's the and thing. This one, and thing. Okay, so there will be double lines for the uh, for this segment. Okay, and then counting numbers. Why we call it counting numbers? So people believe that the origin uh, story that we need numbers, that we discover numbers, is because of the need to count. So counting numbers begins with 1, 2, 3, 4, and so forth. So it's not begin with 0, since if we have 0, we don't need to count, right? So it's 1, 2, 3, and so forth. So the next one will be whole numbers. I'll discuss this because it is different than counting numbers or natural numbers. Whole numbers, we include 0 as the beginning. So start from 0, 1, 2, 3, and so forth. So this is the set of number of whole numbers. The next one is digits. Digits, by definition, number from which the numerals are made. It means that digits, the sets of number of digits only consists of 10 numbers. Okay, only 10 numbers, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's all. So 10, 11, they are not digits. Okay, they consist of two digits, which is, for example, 13 consists of two digits, which is 1, which are 1 and 3. So please be careful. Digits only consist of 10 members. And for even numbers, of course, you can remember it is numbers that are divisible by 2. So both negative and positive. So it starts from this one is the it just goes to the negative, extreme negative, and this one goes to the extreme positive. So it's -6, -4, -2, 0. Okay, please be aware that 0 is also an even number, and then 2, 4, and so on. Okay, so for example, 102 is an even numbers since it is divisible by 2. Odd numbers is the opposite of even numbers, so it's not divisible by 2, but it's still integers. Be careful, so we don't include fraction, we don't include decimals for even numbers or odd numbers. So both negative or positive, as long as it is integer and not divisible by 2, you have odd numbers. -7, -5, and so forth. You can see the examples here. How about the second level? When we go upward on the tree diagram, the first one is the integers. This is the symbols, okay, that we use, the z. Okay, so integers consist of first counting numbers. Okay, counting numbers 1, 2, 3, 4, 5, 0, and the opposite of the counting numbers, which is the negative. So integers includes all of these numbers, okay, both to the negative size or to the positive, continuously going bigger and bigger or going extreme negative, as long as it's not decimals, as long as it is counting numbers and the opposites and 0, they are all integers. Okay, that's the definition. And non-integers are the decimals. Okay, but not all decimals. Okay, be careful. So it must be fractions or terminating decimals or repeating decimals. Okay, so there are decimals that are not non-integers. Please keep that in mind. Examples for fractions: 8 over 9. You can have other examples of fractions. Terminating decimals, just like this. Terminate, it means there is an end for your decimals. Okay, not being approximated. It's just the decimal just have uh, a finite digits. Okay, so next is the repeating decimals. For example, 25.37373737 and so forth. Okay, although it can be seen as an endless decimals, but there is a pattern here which is repeating. So this one also non-integers. Okay, this is also an rational, and I will show you why later. The next one is radicals. Radicals are root of integers. You know, the examples is for square root of 7, cube root of 9, negative square root of 14. Okay, so as long as the negative is outside the square root or not the radicand, you have a radicals. How about square root of 9? How about this one? Well, since you can simplify square root of 9 into 3, okay, which is an integer, so it is not a radical. Again, if you want to classify a number into sets of numbers, you have to make sure that that numbers has already been the simplest form. Okay, square root of 9 is not the simplest form because you can simplify it into 3. So please, if you can simplify certain numbers, before you classify it into certain sets of numbers, you need to simplify it first. So square root of 9 is not radicals. Square root of 9 is integers. It is odd number since it can be simplified into 3. Okay, I hope it's clear. How about transcendental numbers? Transcendental numbers is, well, by definition, you cannot express as roots of integers. So if you square a transcendental numbers, you still cannot find an integers. Okay, so by examples, it's a pi. Okay, it's pi. I mean, it's pi, and then Euler number. Both of these are transcendental numbers, or square root of any decimals, not integers, can be transcendental numbers. The third level, okay, let's go up. Okay, this is the symbols. Anyone? Yeah, we have rational numbers. So by definition, rational numbers are any numbers that can be expressed exactly as ratio of two integers. Okay, so what are the examples? First, 22 over 7. 22 over 7, well, yeah, it's definitely rational since it is a ratio of the integers, which is 22 and 7. Okay, don't tell me that 22 over 7 is pi, since it is not pi. Okay, it is just an approximation value of pi. How about 7? Mr. 7 is not a ratio of the integers. No, that's wrong, since actually 7 can be expressed as the ratio of the integers. How? Since 7 is equals to 7 over 1 or 14 over 2. So this is the ratio of the integers. So as long as you can express it, you can convert it into a ratio of the integers, we have rational numbers. Okay. How about this one? 3.7857. It is a terminating decimals. So there is an end there. Can it be expressed as the ratio of the integers? Of course. Listen. Okay. So this one will be equal to this one. Okay. So you have the ratio of the two integers. And the last one, how about the repeating decimals? The repeating decimals, surprisingly, can be expressed exactly as the ratio of two integers, not being approximated. It's just exactly there. I will teach you in the other video how to prove that repeating decimals are rational. Okay, so let's go further. irrational numbers. So we have rational numbers. So irrational numbers is just the opposite. So since any numbers that you cannot express into a ratio of two integers, we have irrational numbers. Okay, usually it is an endless decimals or radicals or transcendentals. So the fifth level, we have real numbers. So real numbers, this is the symbols for real numbers, and the definition is all numbers that can be plotted on real number line. So as long as that number that you can find where it is on the number line, so you have a real number. Okay. So for example, we have 5 examples here. Negative 3.5. Is it real numbers? Yes. You can have a hint that it is right here. How about negative 7 over 6? Yes, it is right here. How about the repeating decimals? Repeating decimals 0.345555555. Yeah, it's approximately here, but I know it's between 0 and 1. So as long as you can find uh, where it is on the number line, we have real numbers. Square root of 3. Yeah, of course, square root of 3, since it is irrational numbers, endless decimals, yeah, you cannot find exactly the numbers, but you can approximate that the location is around here. Okay, how about pi? Yeah, it's around here. So all of these numbers, if you can find the location on the real number line, you have a real numbers. Okay, how about imaginary numbers? Well, of course, by definition, it's just the opposite. All numbers that cannot be plotted on the real number line is imaginary numbers. Example, square root of negative 6. I just cannot find what is the value of square root of negative 6 on the real number plane, since a square of any real numbers, cannot be negative. How about this one? Negative square root of 7. Negative square root of 7 is not an imaginary number, since square root of 7 is approximately 2 point something. Negative 2 point something, I can detect it's around here. So this is the location of negative square root of 7, right? So it is a real number, not imaginary numbers. So please see the difference. And how about the top level? Yeah, we have complex numbers. So the complex numbers general form is a plus bi, where a and b are real numbers and I is square root of negative 1. We will discuss later about complex numbers on the fifth chapter. So just stay cool. Okay, about this. For example, 6. Is 6 a complex number? Yes, since it can be represented into a plus bi form, which is 6 plus 0i. So 6 is a complex number. How about square root of 7? Yes, it can be represented in the form of a plus bi in this kind of form. Okay, the b is 0. So how about this one? Although this is imaginary numbers, it's also a complex numbers and I can represent it by this form. And this is one more example of the complex number. So in the end, complex number is just any numbers. Okay, any numbers that you find, it must be a complex number. That's the easiest way to figure out.